Yeah.
Okay, so without further delay, let us start our today's class. We were discussing the heterocyclic compounds, and particularly last few lectures we were concentrating on the discussion about the quinoline and isoquinoline. Okay, and today what we'll do is we'll try to cover the remaining portion of this chapter. Okay, so this quinoline and isoquinoline. So we'll be looking at different other reactions in this class. So just to recall what we have discussed in the last class, in the previous discussion on the chemistry of quinoline and isoquinoline, we tried to look into the nucleophilic reactions, particularly the organic, this is IC, organic IC, so IC is missing. So organic lithium reaction or organolithium reactions. We have seen the amination reaction. We have looked into the displacement reaction, displacement of halogen, and a very special reaction, a research reaction we have seen, and its application we have seen. Okay, since you know that it's very difficult to do the Friedel-Crafts type of reactions in the pyridine and quinoline and isoquinoline. So to install the alkyl group at the carbon center, this research reaction we found to be efficient. Okay. Now what we'll do today is today's class will be covering the reactions with radicals. We'll be looking into the reactions with reducing reagents, and we'll be looking the chemistry of oxyquinoline and oxyisoquinolines, and finally we'll be concluding with the quinoline isoquinoline N-oxide reactivity. Okay, so that will be altogether the discussion, the remaining portion of the quinoline isoquinoline. So the radical reactions here, particularly the regioselective substitutions can be achieved at the alpha to the nitrogen. Okay, so remember you have the alpha position with respect to nitrogen. That place is the most suitable place, irrespective of whether it is quinoline or isoquinoline. You have the alpha carbon, particularly for isoquinoline, I will say the alpha and the benzylic position. Okay, that carbon is the most reactive center. Okay, with nucleophilic radicals. So in your first semester, you have come to know what are the electrophilic radicals, what are the nucleophilic radicals. That discussion we had. So what we'll see here, what is the reaction? Okay, how will be achieving the radical reaction? Now, say suppose this is the substituted quinoline. You have the para methoxy para methyl. So 4 position you have the methyl, is the electron rich species. So here, if you treat with this particular substrate with titanium sulfate in aqueous medium with hydroxylamine, okay, and methanol, in the presence of methanol, what happens? This combination, it produces the this particular radical. Okay, this radical, it will be produced. Now this radical is a nucleophilic radical because it can generate. You can see, like, just to remind you, you can, from this radical, if it donates the electron, you can think about the formation of this, which is stabilized, right? Which is stabilized. So what we can tell that this, I mean, it will react with the nucleus. Okay, so that's why you call this is nucleophilic radical. It can stabilize the cation. Okay, the cation form of this radical. If you remove the dot, it will be generating the cation, and that cation is stabilized. So we call this dot can react with the, this radical can react with the nucleophile to give up the electrons. Okay, now since you have informed that the reaction will be at the alpha to nitrogen, so here is you have only one position, so we have seen the formation of this particular radical, I mean this particular product, and you see the yield is quite satisfactory. So you have I mean high yield, 82%. Similarly, if you go for isoquinoline, here if you look at the formation of this radical, okay, and this radical also we call it the nucleophilic radical. Okay, why you have that nucleophilic radical? Because this radical, okay, this radical is this one, so it can produce the NH2 C double bond O. I mean this form you can imagine. Okay, this form you can imagine, and that is stabilized. This is stabilized in both direction. You have lone pair here, you have lone pair here, so you can, it can be stabilized. Okay, you can think like this way, or you can think like you can have C triple bond O NH2. Okay, so these are the stability of the radical, I mean the cation. You can assume. So this radical also, which is suggesting this radical is also nucleophilic. Now this radical is being generated by treatment of Fenton reagent. You have Fe2 sulfate in the presence of sulfuric acid and hydrogen peroxide. This will generate the OH radical, and this OH radical will abstract the this proton, I mean this hydrogen, and it will generate this particular radical, and this radical is nucleophilic, so it will prefer to react. We have the 2 alpha position, but as I told, that it will prefer to react with this interbenzylic center. So you have the benzylic position CONH2. So for my, I mean the amidation reaction you are doing. Okay, you are doing the amidation reaction. So the colors are not visible maybe, so let me rub it out. Yeah, okay. So you have the radical reaction this way. Now quickly we'll go to the reaction, which is one of the most important class of reactions for quinoline and isoquinoline, is the reactions with reducing reagents. Okay, you have seen the reactions with reducing reagent for the pyridine, but here if you look at what we can get it is the selective reduction of either the pyridine or the benzene rings in quinoline and isoquinoline can be achieved. So you can do the selective reduction, whether it is benzene ring or the pyridine ring. You can do the selective the reduction by using the selective reagents. So the heterocyclic ring is reduced to the tetrahydro level by by 4 routes. One is you can utilize sodium cyanoborohydride in acid solution. So this is one route. you use the excess sodium cyanoborohydride in acid solution. So that will be helping to reduce the pyridine ring. Second is by sodium borohydride in the presence of nickel 2 chloride. So nickel 2 chloride, in the presence of nickel 2 chloride, you can use sodium borohydride. That will be helping also for the reduction of pyridine ring. Third is by zinc borohydride. Zinc borohydride itself is found to be sufficient to reduce the pyridine ring. Traditionally, by room temperature and pressure, catalytic hydrogenation in methanol. So catalytic hydrogenation in methanol, that also can be done, like platinum or palladium hydrogen under methanolic condition. That can be also utilized to reduce the pyridine ring. Second class of reagents, the strong acid solution. It is the benzene ring which is selectively be reduced. Okay, so benzene can be converted to the saturated one. Longer reaction times can also do the reduction, full reduction of the quinoline or isoquinoline. That means you will have completely decahydroderivative. Okay, so all will be reduced if you use the reaction for longer time. And third category is the treatment of quinoline and isoquinoline with sodium borohydride in a mixture of acetic acid and acetic anhydride gives good yield of N-acetyl 1,2-dihydroderivative. Okay, so N-acetyl 1,2-dihydroderivative. What does it mean? So you have, this is suppose quinoline. So you are doing N-acetylation, N-acetyl. So you have OMe. N-acetyl 1,2-dihydro. So you have this one will have 2 hydrogen. Got it? So that will be the product for quinoline. Isoquinoline will be just the it will be like this one. 1, 2, remember. So you have N-acetyl AC. This position you will have the reduction. So you will have this product for isoquinoline. Okay. So these are the different reagent system for the reduction. We'll have few more. One is the Birch reduction condition. So lithium in liquid ammonia that can produce 1,4-dihydroquinoline. So for quinoline it will be 1,4-dihydroquinoline production, and for isoquinoline it will be 3,4-dihydroisoquinoline. Okay. Conversely, the lithium aluminum hydride, so LAH, lithium aluminum hydride reduces generating 1,2-dihydroquinoline and 1,2-dihydroisoquinoline. So if we, okay, so another thing is the quaternary salt. If you make the salt from the quinoline and isoquinoline, quaternary salt of quinoline and isoquinoline are particularly easily be reduced. Okay, so they can be easily be reduced either catalytically or with borohydride in protic solution, giving 1, 2, 3, 4 tetrahydroderivative. So you'll have all will be reduced. Particularly, it's talking about the pyridine ring. So structurally, we can show like this. This is the pyridine. I mean, this quinoline, and if you treat with catalytic hydrogenation, okay, there is no acid you are adding, just you are adding platinum catalysis, platinum, and you are doing hydrogenesis in the presence of methanol at room temperature. You will be getting the complete reduction of the pyridine ring. So complete reduction of pyridine ring. And if you use the acidic condition, do the same thing. Use acidic condition like 12 normal HCl you have been used. What we will be looking, we'll be finding that the product will be based on the complete reduction of the benzene ring. So you just look at, you are just changing the acidic, I mean the medium pH, and you are regulating the reaction. Okay. That is done here. And the third one is the important reaction, that is the Birch reduction. So you have the 1,4 dihydroquinoline. Okay, so 1 proposition. So this is 1, 2, this is 3, this is 4, 1, 4. I'm not showing the reaction mechanism. These mechanisms are all well established. So you just need to do what the Bart's reduction, how we can do. Okay, is the electron transfer process slowly, and it will be generating the radical which is stabilized based on that. Okay, and the fourth one is the LAH reduction. So LAH reduction will be at 1, 2 position, and that is because you have the lithium aluminum hydride. So lithium will be first coordinating with the nitrogen, and that makes the aluminum hydride to be close to 1, 2 position. So your reaction will be taking place at 1, 2. Okay, so that is very well known. Now, similarly, if you go for the isoquinoline, you'll have the similar nature. I'm not telling the regular reduction, just Bart's reduction. You have 3, 4. So this is 3, 4 position. So we have 1, 2, 3, 4. So 3, 4 position reduction. And if you use the LAH, you have 1, 2, 1, 2 position reduction. Okay, that you have to consider.
Hey.
Anything you want to tell? Okay, so
no, sir.
Now suppose you have the quaternary salt. So you have N-methylated. Okay, now this one, as I told earlier, its reduction potential is very high, so you can easily do reduction. I mean, it can easily get reduced. And so if you use borohydride, now if you look at in the previous case, if you use borohydride, just bare borohydride without adding anything, okay, we will not see the reduction taking place. Either you need Lewis acid like nickel chloride, what we have told, or if you use the zinc borohydride that are found to be much more reactive. So those things can reduce the pyridine ring. But here, if you do the reduction with borohydride, it will be able to reduce the pyridine ring because this is quaternary salt. So you have N plus, and that can easily be reduced. Now, this particular substrate, if you treat with this one, okay, I mean 1-ethoxyethylene, this one, if you use, you can get this as the product. Okay, I think your diol-solder reduction reactions has already been covered, right? Your pericyclic reaction, Sarah has already discussed, right? Yes or no?
Yes, sir.
So you tell me one thing here. Which one is diene, which one is dienophile?
Quaternary salt is diene and second one is dienophile.
Okay, so this one is diene, this one is diene, and this one is dienophile, right? 2 is dienophile and 1 is diene. Quaternary salt is diene. You have 2 in, and that is dienophile, so it loves diene, right? Like nucleophile loves the nucleus. So dienophile will love the diene. Now I'll ask one thing, who can give the answer? In diol-solder reaction, the reaction takes place by homo-LUMO interactions. Yes or no?
Yes, sir.
So tell me which one will contribute to homo and which one will contribute LUMO. So between these two, which one you have to take as homo and which one will be contributing is LUMO orbitals?
First one, second homo.
First one is homo, second one is LUMO. First one is homo,
Yes.
second one is LUMO. Any other answer? Anybody opposing, or everybody is agreeing with it? Hmm? Is it correct or wrong? One will contribute homo, another will contribute lumo for efficient reaction. So in this case, which one will be what? One is homo, second one is lumo. Is it correct, or you don't know? Hmm? No idea? So in this case, I mean, you have to think one, the homo and lumo, okay, they should have lower energy gap in between. Okay, suppose this is if you extend, okay, this gap has to be low, okay, then only you will have the reaction. If you have far away the homo-lumo gap, the reaction will not be there. Now, how you can bring homo-lumo close? If you increase this one, never forget, okay, if you increase the electron density, what it will do? It will increase the energy level of homo. So energy homo increases. Okay, and if you decrease the electron density, energy level of homo and lumo decreases. Okay. Now you tell me which one will act as homo, which one will act as lumo. Quick. Did you follow what I just told? If you increase the electron density, the energy level of homo will be increasing. And if you decrease the electron density, the homo and lumo will be stabilized.
First and homo.
First one?
Yeah, electron density is for first one. That means energy level is lower level in homo. That means this one also homo.
So you have okay, so let me tell in a different way. Between ethylene and buta want to diene, okay, which one is having a higher homo? Which one is having a higher homo between these two?
Second one.
Second one, sir.
Second one, homo is a high energy level. The first one is homo is low energy level. Okay. Now, if you consider these two, this one and this one, this is butene system, so that one energy will be homo energy will be high than this one homo, right? So this one homo will be here, that one homo will be there. This one LUMO will be now here. This one you have LUMO will be higher, yeah, like this. Now when you are having the electron density more, so this you have the electron density more, okay, this you have electron deficient. So this will electron density will increase the homo level, okay. This will decrease the homo level because you have less electron density. This will decrease the LUMO level, okay. This will increase the LUMO level. Let me tell you in this way. Okay. Now what you have is, if you take this is homo, this is LUMO. If you take this is LUMO, this is homo, what is happening? The gap is increasing or decreasing between this homo LUMO?
Increasing.
Increasing.
Increasing. If it is increasing, reaction will happen or not?
Not.
No. No reaction. So this one LUMO, it is stabilizing. This one HOMO is destabilizing, it is increasing. So your gap is increasing or decreasing?
Decreasing.
Decreasing.
So your condition will be, this is HOMO, it will act as HOMO, it will act as LUMO. Did you get the point?
Sir.
So this one we call the reverse Diels-Solder reaction. Reverse Diels-Solder, opposite. The general Diels-Solder, we generally see the diene acts as HOMO and dienophile act as LUMO. But in this case, we have reverse Diels-Solder reaction. Okay, where diene act as LUMO and dienophile act as HOMO. Anyway, so you will have this as your product. This is Diels-Solder reaction. So anyway, let us move to oxyquinoline and oxyisoquinolines. Now, just let me clear it.
Sir,
Yes.
why this LUMO in a lower level, this first? Why sir doing the LUMO?
No, you have the multiple unsaturation, right? So you consider this one. You have to,
Yes, sir.
not lower in that sense. You just consider this one. Okay, this anti-bonding orbitals is corresponding to this bonding orbital. Okay, and this anti-bonding orbital, I'm just writing a step, is corresponding to this one. Are you getting? Whereas for the regular alkene, you have only one in, you have the bigger one. So this will definitely be lower than this one. Are you following what I'm telling? You have double bond.
If HOMO level is that means LUMO level is also.
This is your situation. Okay.
Yes, sir.
This is the situation. Now what is happening is, in reverse Diels-Alder reaction, since the electron density is more in dienophile, so that will destabilize the orbitals. Okay, so your HOMO will be increasing energy. HOMO initially was there. Since you have electron density more, now it is increasing. Okay, LUMO is, for this particular case, LUMO is increasing also. Now for diene, your is deficient, so it is stabilizing the HOMO. Okay, it is stabilizing the HOMO. HOMO is decreasing. LUMO is also decreasing. Are you getting? For individual system I'm talking about. Now if you consider the reaction, so you have to take HOMO, another you have to take LUMO. Okay. So then you have to do the cross, right? You have to do the cross. You're getting? Now in this case,
that means
yeah, tell.
that means that HOMO is decreasing, then LUMO also will be
Yeah, if you don't have
We,
electron density, if you don't have electron density, the energy levels will be stabilized.
yeah.
And if you have electron density,
Yes.
energy level will be destabilized. Okay. So
Yes.
yeah, so
Yes.
that is the situation. So that's why it's not following the regular one. It just reverse one.
Yes.
Mm. So let us look into the chemistry of oxyquinoline and isoquinoline. Now here what you see is that the quinoline and isoquinolines, in which the oxygen is at any position other than the C2 and C4, for anything you're asking?
Yes, sir. Sir,
Yes.
position of lomophile is or what? Position of dienophile means same. Always.
No, which one? Dienophile means?
That is higher than.
Oh, sorry.
Sir, position of lomophile is same.
It will not be exactly same. You will have some energy gap. Okay, you will have the energy gap. That's why I told you will have the
That energy gap is
more the conjugation.
Energy gap is more than gap between HOMO and LUMO of diene.
Yes. So diene will be always, HOMO-LUMO gap is less than dienophile. Understood? Dienophile, you have one bonding, another is anti-bonding. The diene, you have now similar situation. You have now two bonding, right? And two anti-bonding. Now in this case, you have the gap between these two will be less than these two. Is it clear?
Yes, sir.
Yeah. So that is the thing. Now based on your electron density increasing or decreasing, you have the HOMO-LUMO. Actually, you have to consider now which one will act as HOMO, which one will act as LUMO. Okay. How you will consider the HOMO-LUMO gap? If they are coming closer, I mean the gap is decreasing, then you have the efficient reaction. And if HOMO-LUMO gap is Okay, so what I was talking about, the if you have homo-LUMO gap is decreasing, you will have efficient reaction in diol-solder, product formation. Okay, now that will be governed by the electron density of the substrates. And generally, if you increase the electron density to the diene, the reaction will be regular. But if you decrease the electron density to diene, diene will act as LUMO and dienophile will act as HOMO. Okay, you have to take the electron density increasing to the dienophile. You will get it. So this is the thing. It's very, very important to remember. Okay, and we call under that condition it is the reverse diol-solder reaction. And for oxyquinolines and isoquinolines, here in which the oxygen is at any position other than the C2 and C4 for quinolines, and C1 and C3 for isoquinoline they are acting as the phenol. Okay, they will be acting as phenol. So have an hydroxyl group through they exist in equilibrium with variable concentrations, like it will form the deuterionic form with the nitrogen protonated and oxygen deprotonated. That will be clear if I give the actual form. So say suppose this is one position, you have hydroxy. So what it will do, it will undergo like this form. So you have lone pair, it will, so you have a positive charge here, you have negative, right? Now this one, it will undergo kind of tautomerization. You can tell a proton transfer. So you'll have this form. That is told here. For quinoline, C2 and C4, that you have to exclude. For isoquinoline, C1 and C3. So now, this one, you have lone pair, so it can form like this. So it is now behaving as deuterionic. Okay, so this is deuterionic form. Deuterionic form. Similarly, if you take the 1, 2, 3 position, so 1, 3, okay, 1, 3 consideration, 1, 3, you can have the similar thing here, and you have lone pair, so you can make it this way, and you can have the again deuterionic. Okay, so you can have again deuterionic form. So you can have, sorry, this is will not be there. So you can have deuterionic form like this way. These are important because sometimes the reactivity will be governed by this particular form. Okay. Say suppose you have quinoline, hydroxyquinoline. Now at 4th position, if you introduce the hydroxy group, it will be preferring to have this ketonic form that we have seen in the case of pyridine, right? In the pyridine, you have seen that way. Now this one, if you do the nitration, your nitration will be taking place at this 1, 2, 3 position. Okay, so 3 position nitration. How it is happening? So nitro group NO2 plus will be there, it will be generated, and these will be attacking here. So this way you have the reaction. Now interestingly, if you use the mixed acid at low temperature, it will prefer to do nitration in the benzene ring rather than the the pyridine ring, okay, N containing ring, and that will be para to the nitrogen. Okay, so you will have this nitrogen, so you have kind of amine aniline type, you can think, and it will activate the para position. So you have the para position will be nitrated. Okay, so that will be observed, and that is people have reported. You have this N-methyl system. If you use the Bill-Smear-Hack reaction condition, I think you have know that one, Bill-Smear-Hack reaction, formylation reaction, is very standard reaction. If you use that reaction condition, DMF as the reagent and POCl3 is another reagent. So you will have the reaction at the fourth position. I mean, this 1, 2, 3, 4. So 4 position formylation. So this is happening because you have the reaction here. Okay, so 4th position formylation. And similarly, interestingly, if you use the POCl3 only, don't use the DMF. Okay, so what we will see, what we will observe, you will have chlorination at the center. Okay, chlorination at the center. This mechanism, you should be able to write, because that I have shown you in the case of pyridine. This is one of the important reactions. So these reactions are really important. This Bill-Smear-Hack reaction, this chlorination at the 1 position. Okay, these are very, very important reactions. Some other important reactions, you have carboxylic acid. If it is at the 1 position, it will make the deuterionic form, this one. And now if you heat it, what will happen is the decarboxylation process will happen, and that will generate the negative charge here. So you see the negative charge, and that can act as nucleophile. So if you use any kind of carbonyl compound, it will attack and it will form the alcoholic group there. So you have this group will be formed, or any other nucleophilic reaction you can do. Okay, so this is very, very important. Another reaction, if you have the methyl at the 2 position, okay, 1, 2 position. So this methyl proton is acidic. Why acidic? Because you have nitrogen here at the alpha. I mean, with respect to the methyl, you have nitrogen at 2 position, right? And that nitrogen can act as the electron sink. So the negative charge, if you generate, that will be stabilized. That will be stabilized. That's why the proton is very, very acidic at this methyl carbon. And if you use the some carbonyl compound like aldehyde, what can happen is you have more than 2 proton here, so it will undergo aldol type reaction. So you'll have CC bond formation, double bond formation, and that is here. Okay, so this is one of the important reaction. Similar way, if you use the diethyl oxalate, you will have this keto ester group formation. So it's very simple. You have C double bond O OET, and you have C double bond O OET. So that nucleophilic attack will happen. This minus will attack this minus CH2 minus, that will attack the carbon. Carbon 1 OET will come out, and it will be installing this as the group. Now quinoline and isoquinoline N oxides, the N oxide chemistry. Yes, tell.
Sir, a last one.
Yes.
Don't understand this one. A phenyl CH2. How to attach this?
Now you have CH2 minus, right? From here, what you are generating? You are generating CH2 minus. Yes or no? So CH2 minus.
Yes, sir.
Right? Because you have ethoxy, sodium ethoxide, so minus will be there. That will act as nucleophile, so it will attack here, and OET will come out. Okay, so what it is installing? C double bond O, COET, COET, C double bond O. Getting? Yes or no?
Sir, the phenyl CH2 group, acetyl AC2O.
Oh, this Ac2O. Okay, this Ac2O means
Yes, sir.
you have, this is the anhydride. Okay, this is anhydride. This is not the reagent here. This is used as in this case, if you can imagine, this is used as kind of activating group. Let me tell how it is. So CH2 minus, similar way, CH2 minus, it will attack the benzaldehyde, right? So let me write here. So you have CH2 minus, that will attack the benzaldehyde. So you have PH, C double bond O hydrogen, right? It will be O minus, yes or no? It will be O minus. So you have this formation N, CH2, then you have C, O minus, and you have pH, right? This O minus will attack the acetyl group, okay? I mean acidic anhydride. So you will have, if it is, you have acidic anhydride, it will be becoming beta leaving group. Okay, so this O minus is attacking here, it is coming out. So it is OAC, understood? It will be forming OAC. Now you have, did you get or not? This will be forming OAC. And you have another hydrogen there. So that hydrogen can again be taken up. So this is becoming OAC, pH. Okay, so you have hydrogen again. This is also acidic. Got it? So this hydrogen will be falling, acetic acid will be coming out, you will have the double bond formation. Got it or not?
Yes, sir. Yes, sir. Understood.
Yeah, understood. Okay, so that is happening this way. Quinoline, isoquinoline, N-oxide, quickly let me tell you. N-oxide chemistry is this bicyclic systems largely parallel to the process described in the pyridine N-oxide. So it is similar to the pyridine N-oxide chemistry with the additional possibility of benzene ring electrophilic substitution. Here you have the benzene ring, so you have the chance of benzene ring substitution. For example, mixed acid nitration of quinoline N-oxide takes place at 5 and 8 position via O-chlorinated species, but at C4 at lower acidic strength. So low acidic concentration, C4 position nitration can happen. So nitration of isoquinoline N-oxide takes place at C5. Diethyl cyanophosphonate converts quinoline and isoquinoline N-oxide into the 1 and 2 cyano heterocycles in high yields in a process which must have O phosphorylation. Okay, as a first step, and in which the elimination of diphosphate may diethyl phosphate may proceed via a cyclic transition state. Trimethyl cyanide and as a bicyclo undecane affect the same transformation. Means the reaction you will be looking at, this language is maybe it is confusing you. I'll just tell the reaction, then you will be understanding. But before that, I'll just let me tell another point. The chloroformate and an alcohol convert the N-oxide into the ethers. This is one of the important things. A chloroformate and a Grignard reagent produce two substitute quinolines, and a chloroformate then an isonitride produce two carbomoyl 2-dihydroisoquinolines. Okay, so let us look at the reactions, then you'll be. So you have this N-oxide. This is quinoline N-oxide. If you use the diethoxy phosphoryl cyanide, what we see is the cyano group has been installed here. So cyano group has been installed at the 2 position. So 1, 2 position. So 2 position. Okay. And if you use the mixed acid, you will have the 8 and 5 position the nitration. Okay, in the benzene ring. If you use the chloroformate, ethyl formate, what we see is the ethoxy group will be introduced here. Okay, chloroformate will ethanol, it will be introducing ethoxy group at the 2 position. Similarly, if you take the isoquinoline oxide, if you do nitration selectively, the 5 position will be nitrated, unlike the isoquinoline oxide. If you use the chloroformate, ethyl chloroformate in presence of ethanol, you will have ethoxy at the 1 position. This is the active center. And if you use the diethoxy phosphorus oxocyanide, what you will be having, you will have, let me tell you the mechanism. So first is the oxygen will be attacking the phosphorus, and you will have cyano group will be coming out, and that cyano minus will be attacking at this alpha position. So 1 position, you have cyano group installation. Now you have removal of the oxygen. So that will be the general mechanism. So you have cyano incorporation at the 1 position. In this case, cyano incorporation will be at the 2 position. Okay, so the same mechanism. Got it? So these are the different N-oxide reactions for quinoline and isoquinoline. Just I'll ask one question, who can give the answer. How you will make quinoline N-oxide or isoquinoline N-oxide? Quickly. How you can make quinoline or isoquinoline N-oxide? Can anybody tell? Any answer? Who can tell? So this is very easy, right? You just need to treat with paracid. Okay, RCOOOH. Paracid if you treat, or you can use the hydrogen peroxide also. Okay, hydrogen peroxide and some acid. You can use the acid even in the acetic acid also. Hydrogen peroxide, acetic acid, that will in situ generate the paracid. Okay, and that paracid helps for the generation of pyridine N oxide or the N oxide. Okay, so these are all about the most important reactions on quinoline and isoquinoline. We'll be moving now very fast. We are left with a lot of heterocyclic compounds, but now I'll be very selective. These two I have discussed a bit more details so that you can give more of the answers. Remaining part I'll be covering very fast. Okay, so thank you for, yes, tell.
Sir, if you use mixed acid, then which one is major product? Yeah, both one is.
No, generally this one will be major. Okay, this one will be minor. Okay, but the ratio are not too much varying here. They are comparable. I mean comparable. So if it is 40, I mean you can tell like this is 45% if it is. This one will be around maybe 40%. Okay, they are comparable, but definitely the 5 position will be major in this case, because that will be less crowded and it will be easy to form.
Okay, sir.
Yeah, it's not too varying actually. They are comparable. That's why
Yes.
I mean people have reported. So these reactions, what I am telling, there it is the reported reactions. People have done the reactions and it's reported. Okay, so stopping here. We'll meet tomorrow is the holiday, but if you okay, let us take the break. So day after tomorrow we'll be meeting. Thank you for attending today's class.
Thank you.
Thank you, sir.